Hi. So we've briefly spoken about how the generator and the discriminator play a minimax game in the context of a generative adversarial network. We brought this analogy where the generator is essentially these counterfeit node generating rogue agency, and the discriminator is law enforcement, is the police. There is this a trivial equilibrium, the mode collapse as we call it in GANs, or the Nash equilibrium where both of them exist peacefully in the ecosystem. And we also spoke about how we can think of the noise vector Z, this noise vector Z, as this low dimensional distribution, let's say a normal distribution with 0 mean and 1 standard deviation, mapping each point here, mapping to a high dimensional data points, let's say to an image of a man. Yeah. And one interesting thing to remember is that in GANs, these are called implicit models and not explicit models, because the data is not being seen by the generator directly. So it's implicit, it's not explicit, it's not very direct, because it only gets to see the data through the gradients of the discriminator, which is essentially, the data is kind of encapsulated and encoded in the weights, in the parameters of the discriminator, which the generator then gets to look at through the gradients. So these are the most interesting things about the generative adversarial network. And what we are going to do now is we are going to look at the architecture and then the code of how to build this, and it's very straightforward. So here we start with a vector Z of size, let's say 100, so 100 cross 1. So I'll again draw it here. So this is our input vector Z. Yeah, and this is 100 cross 1 column vector. And then what we do is from here we go bigger, right? So we go to a bigger layer, and the output here is a vector of size 128, right? So we go from, so it's a fully connected, so 128 cross 1. And this is a fully connected with our normal weights and biases. Then this is interesting. What we're doing is we're putting a leaky ReLU on top. This is probably one of the first times we actually use a leaky ReLU. If you remember, a leaky ReLU looks like this. So this is your normal ReLU, but then leaky ReLU also has something in the negative side, right? So instead, so your function is max of 0, let's say 0. So it's usually in max of 0, x, but here it's maybe 0.1, x, right? So this is what your leaky ReLU usually looks like. So then what we do is, so we started with our Z vector, our small Z vector. So this is, let's say 100. From 100 we went to 128 using a fully connected, right? From 128 here we put a leaky ReLU, and then the output of the leaky ReLU, we then put it into another fully connected, and from 128 we go much bigger, we go 32 cross 32, which is 1024, because 32 is 2 to the power 5, so 2 to the power 10, 1024, so 128 to 1024. And here we put a tan H, and I'll tell you later why we do tan H, but tan H is essentially to squish everything in, so tan H will look like this, and this is essentially to squish everything between -1 and 1 range. So no matter what the domain, no matter what the output of the previous layer here is, the outputs will all be between -1 and 1, and this is why we use tan H, because this is how we also normalize data, but I'm going to talk about that. And that's it. That's all what our generator network looks like. And the discriminator is then very straightforward, right? So to the discriminator, we have this 32 cross 32, which we got from the generator. We, like always, we go from here to a little bit smaller. We go to 128 cross 1, and this is again weights and bias. And then we put a leaky ReLU. So we have a leaky ReLU here, right? And then we do a fully connected again, but we now bring it down to very low. We bring it down from 128 to just 2 cross 1, because this is also our final output. And on top of this, we do our regular, right? We would do the soft max, and then we do the cross entropy. So this is all that there is in our generator and discriminator networks, and I'm going to now show you code, right? So before I show you the code, let me show you the data. So we'll start with like very simple MNIST data. We've used it in the past. MNIST, we load the data set in MNIST underscore X. So it's first start with its unsigned character, so we convert it into float and we divide it by 255. What will happen when we do that? Every thing will be between 0 and 1, right? Because it was between 0 and 255, we loaded it, element wise we normalized it, so it became between 0 and 1. Then we subtract 0.5 and multiply it by 2. What will happen? What will the max and the min be? Well, now the max will be plus 1 and min will be minus 1. Then we always we need to visualize our data set. So here we visualize the first 42 elements of our data set and it looks good. It looks like, okay, it's shuffled, it's loading the right images, so we are happy with it. And we also remember the data set size. The data set size is 60,000. And we also remember the dim size. The dim size is essentially 32 cross 32. So dim size is 1024. Also remember how we don't care about the Ys, right? We don't care about the labels of these images themselves, because here our goal is to simply generate the image itself and has nothing to do with the label. So we now define the generator and discriminator network. The generator network is straightforward. We call it model underscore G. Our hidden layer, our hidden parameter is 128, so our hidden layer has 128 neurons. We use sequential. So inside this, we, like we said, we do 100 cross hidden. So we start with our 100. We go from 100 to 128. On 128, we add a leaky ReLU here, right? So we have a leaky ReLU here, and then from there we go to 32 cross 32. So we go to 32 cross 32, which is 1024, and here we have a Tanh, right? And this is what we looked at. And the discriminator network is even simpler. We just take these 1024. From there we go to number of hidden. So we go to number hidden, which is 128. From 128 we go, so we obviously put a leaky ReLU, and then we go really small, we just go to 2. And here on top of this we have our cross entropy with softmax and everything. So that's all that there is. We now define two functions. One function is to essentially get a real batch of data, and one is to get the fake batch. Fake batch, what does it mean? It means you're getting it from the generator network. What do you need to give it? You need to give it your Z. We are giving it batches of Z, so we give it batch comma Z, and we forward all the random data and then give a batch of images out, a batch of data points out. Similarly here, what we do, we give it this data structure and we populate this data structure with real images. So we go from to batch size, we do a loop, and we then populate this data structure with the image in the data set at location ID, and simply flatten it so it becomes dim size. And if you remember, dim size was 1024. So after you do this, your batch data looks like a matrix where every row is your image. Let's say this is image 1, this is image 2, and so on, and all of them are of size 1024 because we have flattened each image into a row. Okay. Now we are setting some hyperparameters up. We say, okay, we want to use cross entropy. Our batch size is 32. Our half batch size is 16. Batch data is this data structure which we spoke about in the last slide, right? So it is of size batch size, which is 32, cross dim size. Dim size is what? 1024. And then we have targets. So targets are just vectors, right? These are so you have your target underscore D. So target underscore D is for the discriminator, and that is a full sized batch. It is 32 cross 1 because you'll have both real and fake. And then you have your target for the generator. This is what we use to train the generator, and this is only half batch size because here we only have fakes, right? All of them are just fake data points. And we also then have our optimizer. Our optimizer, we use Adagrad, you can use Adam, but don't, like, HGD doesn't work as well because learning is harder in GANs because it's a very sparse signal. We also have our optimizer state for the generator and discriminator, and we also have the parameters that we actually change. So on top are the parameters for the discriminator, and these are the parameters for the generator model. Okay. So next we are gonna essentially do the two loops. So this is the outer loop. Here we go all the way, to the maximum number of epoch, and the inside loop is one epoch itself, right? And let's see what happens in this inside loop. In the inside loop, in the first line, what are we doing? We are sending it this data structure that we had created, batch data, and asking it to fill, asking get real data to fill half of this with real data. Okay, so we have our data structure called batch data, and we are filling half of this, the first half of this, with real data, right? So we are filling it all with real data. Batch data, what is the size? It's 1024 is the size of every row, and it has 32 of these rows, right? Now first 16 we are filling it with real data, and then let's look at what we are doing in the next part, right? So we are then also creating our random data. Random data is essentially a batch of Z, and how many are we creating? Half batch data times, right? So we are creating 16 of these Z's. We are this is of size 100, so this is why that 100, and we are subtracting 0.5 so that it's equally distributed around 0, because when you ask torch.rand to give you random numbers, it will give you between 0 and 1. So we are subtracting 0.5 to then have it equally around 0, so between minus 0.5 and 0.5. And then what do? We call model G underscore colon forward. So we are essentially giving this random data, 16 of these random datas, and then in this batch data structure, in our data structure this one, we are then from batch size half plus 1 to batch size, meaning this second half, we are filling it with these fake images, right? So the images generated from the generator. So we now filled these with fake images. We also look at how we fill our targets. So the targets for the discriminator is straightforward. The size is again 32, and the first half is filled with 1, which stands for real, and the second half is filled with 2, which stands for fake. So this is what we are doing when we are doing your discriminator. But look at what we are doing with, so this the size of this is 32 and each of them are 16. And now our target underscore G, if you remember, the size was 16 cross 1. And what are we filling it? We are filling it with 1s. What was 1? Real, right? So we want the loss to be computed for the generator with respect to real. We want to ask what will it take for us to get real? What is the loss based on that, so that we can back propagate, not update within the within the discriminator, because that will be wrong. Use the discriminator to take the gradients into the generator and then here update the weights. Okay, so we have now set up our data. So this is our data, and these are the two labels, one for the discriminator, one for the generator. And now we simply need to call the optimization functions, right? So the so this is the discriminator and this is the generator. In the discriminator, what are we doing? We are doing simple things. We are forwarding the model discriminator, so we are getting the output of the discriminator for our batch that we have prepared. Our batch is this. And then we compute the loss of the discriminator. We then backpropagate through the discriminator and update the weights of the discriminator, right? So here you see that we are updating the weights of the discriminator. And this discriminator training is straightforward. It's just like training a binary classifier. Nothing difficult. The generator is where things are interesting and different from what we have done in the past. What we are now doing is we are putting the output, so our random data, right, random output, which we put in the first part of our batch data, into the discriminator, and we are computing the loss, you see, with respect to the targets of the generator. Remember this one, so all reals. Then we compute the loss. We go back into the loss, so we backpropagate through the loss, and then we backpropagate it through the entire discriminator. And then we take the input gradient at the input of the discriminator, put this input gradient here. You see, this one and this one are same, and here we are back propagating through the generator and actually updating the weights of the generator, right? And that's all that there is in a generative adversarial network.